forgot how much I spent, like $19, $18, and I bought 2 of them. Urgh. Should yell at Amazon. But anyway, on the notes that I used, there's the 3 websites that I picked from, and now I'll go to those notes and reference it. Didn't want to come out of left field. Eventually, we're going to be doing what's called the empirical rule. That's the mathematics are going to do. But then after talking about this yesterday, it seemed that a lot of students had already heard of this stuff. So I actually turn this, if I keep my face and see what we're looking at as notes here. So what is a density curve? Okay, so I'd have to explain that first before we do the empirical rule in math. And really what it represents is probabilities, right? And the area under this curve is actually the probability of an event happening in a certain specific scenario. So a density curve is a graph that shows probability. What is the total amount of possibilities for an event to occur? 100%. All right, so that's why the area under this curve all is equal to 100% or 1, meaning moving the decimal 2 places. I got my left and right to the left. All right, 100%. To change that to a working number, you move the decimal 2 places to the left. So that's what that says up at the top. Really want to focus on this. And then this is the fascinating concept. And then a couple people last hour or yesterday, your yesterday group, remember this. And actually, this must be something you've heard before. When you collect a lot of data of certain things, the data tends to, remember the law of large numbers, formulate itself into a bell curve. All right. And actually, a very symmetric bell curve, which we'll talk about in a minute. So here's a for instance. I think this was weight of males just on average. So the average weight appears to be like 200 pounds for the average male. So that's why you see right at the top of this would be called the mode, and actually the median and the mean. This is kind of like a situation when you have a normal curve, when you have this perfect bell curve, which doesn't always have to happen. So then what happens when we, what's the probability if I select a male and they have a weight of 275? Well, just statistically, probability wise, that probability would be low because it's not likely because there's not that, as many people that weigh that. And then going further, 300, and so on and so on and so forth, less likely to occur. So that's what you're looking at. That's what that graph means. And I'll wait till that goes here. I want you to mark this up too, because this may very well be a test question. The idea of skewed left and right. And this is one of the greatest images pulled from this website I've ever seen for skewed left and right. This is not a normal curve. This one is skewed. Now, the reason they call this skewed left, as I read on this website, is it tails off to the left. Okay, that's one reason. Another reason is mode is the most occurring, which is this high value right here, right? But the mean and the median in a skewed left scenario, the mean is less than the median. And this is what, there goes my pen. Yay. Every day. That wasn't a bad one, but hopefully it doesn't get worse. So notice that, and remember these are x-axis values. So when you look at that weight example, 200 was right in the middle, 300 and 100, it's x-axis values that go up as you go right. Whereas where you're skewed right, these are non-normal curves. It tails off to the right. In this case, the mean is greater than the median. And these are things that statisticians do care about. Where's the mean compared to the median? And it tells them some stuff. But we're not going to worry about that too much more other than that, the idea of skewed left and skewed right and what it looks like. I do want to go to this website next. Now, if you open up my PDF of these notes, these links actually work. I like that about PDFs, but I'm going to go to the calendar again. Examples of real world distributions, just a couple. I just searched what kind of data ends up being a normal distribution. This was the fascinating thing that I learned in stats. The more and more data you collect, the law of large numbers. Let's go back to the guessing the beads and the carnival from the movie. The more guesses you get, then the average of the guesses get closer and closer to being correct. And the guesses would actually start formulating a perfect normal curve. It's fascinating, the law of large numbers and how that occurs. Of course, you get some goofball, crazy guesses. Some people purposely guess, 1 million. Well, that's going to be a far out outlier that will be in the data, but will not affect that too much, or maybe thrown out because of the idea of an outlier. It's a goofy guess, but certainly the more guesses you get, that would come close to a normal distribution. Fascinating. All right, so normal curves. There's your our rule that we're going to be dealing with here. But height, as long as you get a whole bunch of people in the data, then the average height of people would end up being in a normal curve, law of large numbers. So there is a certain average height, and then somebody that's really tall, that'd be less likely to happen, just like very short as far as selecting someone. What's the probability I select someone and they're 7'9" tall? There's not that many 7'9" tall people. They would be at this far end of the normal distribution. Again, just trying to help you to read it. In the movie, they talk about rolling dice, right? And then it's very unlikely to get a pair of ones. There's only one out of 36 chances for that. When you roll two dice, there's 36 possibilities. But to get a 7, that's the most likely occurrence. So the more you roll, if you roll 1,000,000 times, then more than likely these are the likelihoods that would come out. All right. And it would be normally distributed. Tossing a coin, they talked about that. IQs of people. Albert Einstein, who just Stephen Hawking. There's not many of those people, right, that have those IQs that are able to do the things that they did. So, what's the probability that I select someone and their IQ is 1,800? I don't even know if that's a number, but blah blah blah. Stock market, so stock market analysis. And actually, when you look at this, I'm not going to be able to go over this too much, but probably on Monday on my calendar. I haven't gone over these things: stats, careers needing stats, why stats. Kind of the thing that I'm going over right here. If you're going to be a business major, you're darn right. You're going to have to know statistics. Shoe sizes, just like height, birth weight, probably just like height as well. Student averages. I'll end with this one. Tuesday, the juniors are taking the SAT. Absolutely. Part of their results, there's a graph and it tells you like what percentile you lie in. But then also, the SAT, there's a certain average that you get, and that's where the majority of the grades are. And then some are better than that and some are worse than that. And then it actually is a normal curve that represents. Law of large numbers. Okay. With all that being said, there's the why. So what I want you to write on this is maybe some variables that I'm going to change a little bit. Can everyone say mu? Yeah. What are we all, cows, right? No, I'm just kidding. Mu is actually like an M in Greek lettering, and that actually stands for mean. Okay, and I'm going to do it. Mean of a population. Before I used X bar. That is mean of a sample. And I just want to be the good stats teacher telling you that. You don't have to worry about it too much more than that. Boy, good L. That is not the pen's fault. That's Mr. Samuelis. What I'm going to show you next from the website, they changed X bar to mu for our next drawing, and it's not a big deal. They both mean mean. They both mean average. So let's just get over that. So in a normal distribution, here's what's true. Actually, the mean equals the median and actually equals the mode. The mean is the most frequently occurring value. All right, so that's why that is at the very top of that curve. And we will call that, well, we do call it 0, but that also standardized, we'll call that mu now. That is the mean. And 0 is its z-score, right? And that's what we talked about before. All right, and I'm not going to put this in terms of the standard deviation symbolism. Standard deviation is that lowercase sigma, and that is the standard deviation. But all I'm going to do is say this. This is 1 standard deviation, this is 2, and then this is approximately 3. And then to go left, and I'll zoom in on this as people are trying to look at that. This is -1. Try to get this symmetrically looking good. -2, I don't know if I've done the job, but -3. Just remembering that from last week. We already did these things. We talked about z-scores and what it means. It means how many deviations you are away, both left and right. What time do we get out of here? Is it 13? No, we're doing excellent. So all this is set up so your brain is just like, why are we doing what is going on with these numbers and what's happening? So that's the next page with what we're actually going to cover. Okay. Now it's finally to the math that you're responsible for. And hopefully you understand what you're looking at now. By the way, this is the backbone of statistics. Like when I taught statistics, we do a couple things to build up. This is one of the buildups. We've always done this like in Math 2 or Algebra 2, kind of introducing this in case a student 2 years later takes stats. And then we deal with these standard normal curves like almost the rest of the year. And do some calculations, different formulas, different things, and then some other things. But at least it's a major component. Okay, so empirical rule. This, first of all, put this up here right now, and I'm going to hammer it 3 times at least. This is an estimate. This is just a ballpark kind of general idea of what happens with standard normal curves. On Monday, we are going to talk about specifics using a z-score table, and I will hand you that table. So Monday's about working with a table and not this empirical rule. So I want you right now to remember that this is separate from what we're going to do Monday, and I'm going to reiterate that in our notes. But the empirical rule is an estimate. So notice where there's some other words in here. The rule is a statement about normal. No, okay. Referred to as the 68, 95, 99.7 rule. Here it is. That's what I was looking for. Roughly. So in any normal or bell-shaped distribution, roughly, that just means about. This is about what happens, kind of. All right, very, very, very close. Okay, so here's what happens. 68% of the observations stand 1 deviation from the mean. So 68%. Then notice my notations down there, not mine, taken from the third website, which I really liked what they did. We're going to break it down even further to the right. That's why I have that blank normal curve there. But notice our notation, a much better mu down here. All right, that's mu. It's like an M, but real fancy. And then that's what I said there, plus 1 deviation to the right. By the way, that's deviation of of a population as well. You don't have to worry about that. Okay. So blah, blah, blah. 2 deviations to the right, 3 deviations to the right. Almost choking myself with this thing. I just bought a new one of these after spending so much money on those other microphones. Trial and error, I guess, costing Mr. Samuel some cash. I have an exposed wire right here too. I'm afraid I'm going to electrocute myself during the notes. So if that happens, don't just let me lie on the ground. Please tell someone. Don't just wait for the bell to ring and then leave. Next, 2 deviations from the mean, 95%. And then 3 deviations from the mean, 99.7%. What's left over, folks? What percent's left over that hasn't been accounted for? 0.3. This is the Stephen Hawking's, the Albert Einsteins, right? Okay, so what do I have to do with 0.3? There is something past 3 and -3 deviations. This is the beyond the norm, like way off, way different. All right. So we'll talk about that when we break this down further. Here's something more valuable. We're going to redo this. And I'm not going to do mu. I'm not going to do that. I'm just going to do the numbers. So here's a z-score of 0. Remember what I'm writing here. That's what z-score meant. What I'm going to do is try to symmetrically and match this as much as possible. 1 and -1. What we're going to do is get each one of these individual quadrants and what the percents are, right? And that's really what you need to focus on for our next thing. Hey, everybody, if this is 68%, what's that percent and what's that percent? 34 and 34. So the first one's real simple. This is 34% of the data. This is the other 34% of the data. And actually, when I opened up that website for standard normal curves, they had this picture with the 34. But here's the thing, and I want you to understand this. And there is a problem with this, and it is part of what all teachers make you do. Heck, when you take anyone taking anatomy and physiology, yes, isn't that like a million vocab words you got to memorize, like muscles and blah blah blah. You have to memorize these three numbers. That's all I'm asking you. Not asking you 20 muscles on one page and then go to the next page. It is a job that people ask you to do, and it's allowed. So you're going to have to memorize the 68, 95, 99.7. Lock it in. Because then on a test, you're going to want to do what I'm doing here. As long as you remember the 68, 95, 99.7, you're going to be fine breaking down these quadrants. So the first one's easy. The second one, 2 deviations. Just make mathematical sense out of this. I've already taken out 68%, and now I need to figure out what's left over here and here. Well, all I need to do is take 95 minus 68. So I'm going to put that up here. And then do what, everybody? Divide by 2. It ain't rocket science. This is Math 101. Just looking at what area is left over. And I believe you get 13.5, right? All right. And then maybe I'll change colors. Green, I need this little area from here and there. Well, I have this accounted for, all right, or that is 95%. So what would 99.7% be when I'm doing this? It's the same thing. You take 99.7 and you subtract 95 because I want to get that 95 out and see what's left over on those last two quadrants. Oh, what is that? Is that 4.7? What's that divided by 2? 2.35. Okay, then this is how I'm going to write this because this area is so small here. I'll write this as 2.35. And notice I'm writing these as percents. When we go to our next example, sorry, I didn't put 2 and negative 2. And I forgot to put 3 and negative 3. This is 2.35% here as well of the data in that little quadrant right there, if you want to call it a quadrant. But this isn't everything. 99.7% of the data is accounted for. So what happens after these values? This is the, I don't know why. All you do on this one is take 0.3 and divide it by 2 because you're missing 0.3% of the data. And 0.3% of the data is divided up into those last two tails, all right? Which is 0.15. Now remember, this is 0.15%. So I'm going to verbalize this and then write this on the next slide or next set of notes. 34%, everyone knows, is 0.34 as a decimal, and that's simple. All right, 13.5%, 0.135. Problem is when we get to these last two, 2.35 is 0.0235, right? Not 0.235, that's 23%. 0.15% is 0.0015, all right? So there's your percents, 101. All right, and then notice at the end here, again, I said I'd do this like 3 times. Students tend to use approximation. So this is an approximation for a real quick thing instead of more precise values found in tables. I'm going to give you a table on Monday. We're going to change this a little bit. So for using software, the empirical rule should be used as a quick estimate. So I've hammered that down 3 times. so that when it comes to the test next week, which we're shooting for Friday, I'm going to have empirical rule questions, which you use the estimate feature. And then I'm going to use specific questions where you have to use a table and a chart. Okay. And you need to understand that that is separate. All right. Then I'll tell you another reason why, the empirical rule only really helps you in certain specific scenarios. I'll tell you that during this example. Okay, so an adult IQ scores are normally distributed with a mean of 100. I guess 100 is the IQ score. I said something like 1,000 something, I don't know. And a standard deviation of 15. Okay, great. Find the probability that a randomly selected student has an IQ of, or, and then between, more than, less than. This is really a big deal. This feels like, why, more than, less than, between, what's going on? This is a big deal in stats. There's different types of tests, and you have to know between, you have to know at the tails, like what's going on when you're looking at a normal curve. So this is a wax on. Anyone? Wax off. Just do it. Mr. Miyagi. Okay, so the first thing you should do is make your graph. Okay, so reading the question, let's actually get specific values here. So this is 100, which is a z-score of 0, by the way. But we don't need that right now. We don't need z-scores for this particular scenario. We can mark this up like you've already done. And then add 15. Add 15. And then add 15. And then subtract 15. Do the best you can on your standard normal curve, like what it looks like. Subtract 15. Subtract 15. And then here we are in a test. Let's pretend this is a test. All right, the empirical rule. Oh gosh, okay, what did I have to have memorized? All right, I got it. I had to have memorized 68, 95, 99.7. Please really lock that number, and that's probably the hardest one to memorize. You might say 97.9 or something. Do an old dyslexia switcheroo there. I often do that sometimes just in general. Oh, I flipped that around in my mind. Okay, all right, that's easy. All right, so I remember this now. So that means this is 34%, and this is 34%, half of 68. Okay, yeah, I got the ball rolling now. Remember the next thing that Mr. Samuel said to do. So to get, this is 95% from here to here. I got to get that 68 out and then divide by 2. Okay, yeah, I remember 13.5%. Stop. I'm actually going to make these decimals. Okay, so let's officially do that. So let's make them 0.34 and 0.34. And then I'm going to go ahead and totally erase 13.5 because, what just happened there on the video? All right, 0.135 and 0.135. And then the last one is 99.7 minus 95 divided by 2, all right? So you get 4.7 divided by 2, which is 2.35, but that's point. You know what? I'm going to do this like this. 0.0235. 0.0235 to hammer down the point of how to deal with percentages. All right, and then the last tails after this, these little barely likely to happen situations, 0.3 divided by 2, which is 0.15, but that's 0.0015. And this is 0.0015. These all add up to 100, or I'm sorry, 1, now that I changed them to decimals. Once you got this done for this question, then you can proceed on and answer these questions. Now, here's another reason why the empirical rule works for this. 70 is spot on, right on 2 deviations. Imagine if they asked between 83 and that z-score is not directly 1, 2, or 3 or -1, 2, or 3. The empirical rule wouldn't work. The only way the empirical rule works is if it's exactly on one of these deviation levels. Sorry if I'm boring some people. Some people are rolling their eyes. 70, love that, to 115. This is all you got to do. The percentage of that happening is 0.135 plus 0.34 plus 0.34. And you can do those calculations now. Now it's Mickey Mouse simple stuff. More than 85. We're going to really hammer these kind of questions when we get to that chart on Monday. More than 85 is all of this. Here's what my seniors screw up. They always forget that last little chunk. They always forget the 0.0015. Do not forget that 0.0015. After this, it's a Mickey Mouse question once you get your values down. Then this last one is kind of annoying. Less than 130. That is all of these. I actually have a better way of doing this. Better way and faster way of doing this is doing the opposite of this. Taking one, which represents 100% of the data, and subtracting the opposite of less than 130, which is greater than 130. 0.0235, and don't forget that 0.0015. Okay, so hopefully you understand that green, right? Instead of adding all of those up, we could take one minus the other possibility, the opposite of it, those probabilities. And one represents 100%. Then the last one, good. Oh, people putting their stuff away with 3 minutes left. Love it. If you surveyed 1,500 adults, how many would have an IQ between? Okay, let me just use a circle for that instead of a highlighting that to screw up the other ones. 100 to 145 are these three percentages. So those three percentages are 0.34 plus 0.135 plus 0.0235. Okay, so now I got the probability that that would happen. Now, if I surveyed 1,500 students, how many would have that IQ level? 1,500 times this decimal. So really, it's just that decimal that I end up with times 1,500. And about that many people would have that IQ, because that's the probability that that would happen, according to the standard normal curve. Okay, so hopefully this is not a big deal. This really sets up what we're doing all next week, but not with the empirical rule, with a chart of z-scores. All right, much different questions pertaining to that. Alrighty then. Oh, I'll stop the video. Hopefully that really is easy, because it actually is. You just have one little thing to memorize.